Velocity vector in projectile motion. How does the velocity vector change and not change for a projectile? Projectile motion occurs when an object is given an initial velocity at the beginning of its freefall motion. So that means it's launched, it's shot upwards, it's thrown if you're throwing a basketball. This initial velocity, labeled v0, must have a direction that is not straight up or down. If the initial velocity were straight up or down, then the object would just move along a vertical line rather than a parabola. And if it's in a vertical line, then the only thing you've got to worry about is just the force of gravity, which could also be true for a projectile. If it's launched and then the only force acting on it is gravity, then we're still in free fall. But projectile motion is a special type of free fall in that there is an initial velocity given to it. So it's shot up. And that initial velocity happens in the x direction and the y direction at the same time. We'll get more into that. The object would also move down along a vertical line if the object is released from rest, so there's zero initial velocity. We're often given the initial speed, v0, and the initial angle of motion. And that initial angle of motion is relative to the ground. So if we take that angle relative to the ground, then we can look at the velocity happening in the y axis, which is the vertical axis, and the horizontal axis, the x-axis. To make projectile motion easier, we're going to change the speed and direction into these separate components. Components, remember, just means pieces. So we have this leg of the right triangle and this leg of the right triangle. If we think about a graph, then the x and y axis are always at 90 degrees to each other. So it's very useful for us to take an angled vector and break it down into these x components and y components because they're at a right angle to each other. If you're at a right angle, then you've got a right triangle, and now we can use any of those right triangle rules that we know, and we can easily pick apart this triangle to solve for whatever it is we need. We're going to calculate these components exactly the way we calculate components for any other vector. Remember, the magnitude cosine theta happens along the x, and the magnitude sine theta happens along the y. This only happens because the angle is relative to the ground. If the angle were relative to this vertical line right here, that changes the whole triangle. Then this becomes the adjacent, and this becomes the opposite side. Okay, so just remember that. It's okay to think about magnitude cosine theta happens on the x and magnitude sine theta happens on the y, as long as you realize that's because this triangle. And as we go further through Unit 4, you're going to see that switch to where we're actually looking at angles from the vertical axis. Alright, so velocity changing during projectile motion. Once the object becomes a projectile, the horizontal velocity will stay constant. Look, it's 30 meters per second the entire time. Because gravity doesn't pull us left or right, gravity only is acting downwards. So the Earth is pulling us down. Okay. The vertical velocity decreases by 10 meters per second because g equals 10 meters per second squared. So, velocity decreases by 10 meters per second every second because g equals 10 meters per second squared. So we started out with 40, then 30, then 20, then at the top we have no vertical velocity. So our vertical velocity in the y direction we would say is 0. But that doesn't mean the object is stopped, and it doesn't mean the object is not being accelerated, because it still has that 30 meters per second in the horizontal. So it's still moving horizontally, and it's still being accelerated downward, because gravity is the only force acting on it. So gravity doesn't stop just because we've reached the maximum height of our trajectory. Gravity is always going to be there. In this animation, the components of velocity are printed in gray every second. See how the horizontal stays constant and the vertical goes from 40 to 30 to 20. The highest point, the vertical velocity, is 0. Then the vertical velocity becomes negative. Negative 10, negative 20, negative 30. as the downward motion becomes faster and faster and faster in the downward direction. Projectile motion is two motions. One motion is horizontal, constant velocity. The other is vertical, constant acceleration. They're both happening at the same time. Projectile motion is actually two motions. Horizontal, constant, we just said this. In the vertical direction, the motion is constant acceleration. Again, from here, let's look at what these dots are. Watch this animation. Note the ball is launched horizontally, so the launch angle here is 0. That means the ball has no vertical component of initial velocity. Because the launch angle is 0, we could take our initial velocity of whatever it is, 25 meters per second, and then sine times sine of 0 will give us 0. In other words, if an object is launched horizontally and then the initial velocity in the y equals 0, then the initial velocity in the x will equal the total initial velocity. It's not being split apart. It's not being broken down into smaller pieces. All of the initial velocity is just happening in the x direction. There's a white ball that goes across the top with the projectile. This white ball is the horizontal motion. See how it's constant velocity. The white ball makes a gray dot every second. So those dots make a motion diagram. The dots are evenly spaced apart, showing that the horizontal motion is a constant velocity. What's happening in the y direction? Well, we've got small space, and then bigger space, and then bigger space, and then bigger space, and then a bigger space. So what does that mean? It means we're accelerating. We're getting faster and faster and faster going down. Distances are proportional to squares. This shows the vertical motion is constant acceleration. Because projectile motion is two motions, one is horizontal and one is vertical, we need to have two sets of equations, one for horizontal and one for vertical. We start with the equations of motion as printed in the AP Physics equation chart. So we have Vx equals V naught x. A lot of the students have been confused. What do these little subscript x's mean? It just means everything in this equation has to happen along the x-axis. If we were dealing with a y-axis, then everything in this equation has to deal with a y-axis. It has to happen separately. Even though it's happening at the same time, they have to happen separately. So that's what these little x's are. We've got our velocity time equation, position time equation, and the note time equation. Note that little x subscripts mean we're seeing horizontal distances, horizontal velocities, horizontal initial velocities, and horizontal accelerations. Gravity is not all horizontal. Gravity is totally vertical. So for horizontal motion, we make a sub x equal to 0. That gives us all of that junk goes to 0. So we're left with the final velocity equals the initial velocity in the x. All of this junk goes to 0 if a is 0. Then that gives us this shortened equation. For this one, all of this goes to 0 if acceleration equals 0. So we're left with the final velocity squared equals the initial velocity squared. First and third equations are completely useless because they tell us the vertical velocity is the same as the entire projectile motion, which we've already said. And now remember, this will change as we introduce air resistance into it. But the middle equation is useful and will be our horizontal motion of equation. Horizontal equation of motion.